Okay, so today we are going to discuss about nonlinear dynamical system. So let's start. Okay, so first we're going to see what is nonlinear dynamical system. In order to understand that, first let's see what is system. Okay, a system is a thing, a collection of things which we are interested to analyze. Okay, so whatever we are trying to analyze, and we consider that as a system. Okay, and the rest of the thing which are other than the system are known as surrounding. Okay, so now the a set which consists of the system as well as the surrounding is known as universe, and the boundary between the system and the surrounding is known as system boundary. Okay, so these are the definitions which we have borrowed from thermodynamics. Okay, so that's what the system is. Okay, now the system has to be represented somehow, right? And that will be represented by the state of the system. Okay, so the system is in what state, right? In order to describe about the system, we need to describe about the state of the system. Okay, somehow we need to represent the state of the system in a mathematical form, and that we do by a set of variables. Okay, so here the set of mathematical variables, maybe each number is a real number. Okay, so here let's say that set of variables n variables. Okay, I could represent by telling what are those n variables. I could represent the state. So the same thing can be written like a bold X in order to represent that it's a vector. Okay, so an example, let's consider a spring mass system. In the spring mass system, the position of the mass could represent it on what state that system is, that spring mass system is, right? So that's spring mass system is a system, and representing where the position of the or where the mass is the state of the system. Okay, and that variable is a state variable. Fine. Another example, in an electrical circuit, say there is a resistor. Okay, and the voltage across the resistor could be one state of the system. In another sense, we could also say the current flowing through the resistor could be another state variable. Okay, so that's how we represent the state of the system in terms of the state variable. Okay, now this state variable, the collection of state variables are represented by a bold X, right? Big bold X. And if that X, if that state variables is changing with respect to time, which is represented by t, small t, then that system is known as dynamical system. Okay, for example, again in the spring mass system, the position of the mass is the state variable, and that's varying as a function of time when we give an initial excitation, right? So that's a dynamical system. And in this example, or instead of resistor, if I put a capacitor, in order to charge that capacitor, okay, then the voltage across that capacitor is keep on varying when the capacitor charges keep on changing. Okay, so that's the voltage across a capacitor in that circuit is a dynamical variable. Okay, so yeah, so these are the dynamical variable, and if that state variable is changing with respect to time, then the system is a dynamical system. Okay, now so in order to understand how the system is going through with respect to time, what I want to know is how the state variables are changing with respect to time. So basically what I want is, I want to have my state variables as a function of time, like this. Okay, so that's what I want, but the physics, okay, will tell me or will give me only the governing equation in this form. Okay, so only by solving this I'll be able to get this one. So I will have it in this form where the x dot, which means at what rate the state variables are changing, so that's what x dot means. Okay, and that x dot, it's not necessary to be constant, that change could also vary with respect to time. Okay, and it depends on what? It depends on these variables. So the first x, which means it depends on the current state variable. Okay, the change of state variable depends on the current state variable. Okay, what else? Zeta. What is zeta? Zeta is a history dependent variable. So what is this history dependent variable? This is the current variable, right? X is a current variable, but how that current variable has been achieved, right? So what is the history that system gone through? So this rate could depend that on as well. If we have to account the history, then I'm introducing a new variable zeta, and I'm introducing that dependency. Okay, so that's why I'm introducing zeta. Okay, and also it could depend on time. Okay, at this point you could ask, wait, this x itself is a function of time, right? So which means it's automatically a function of time, then why do I have to put t explicitly, right? So the answer is if let's say there is an external disturbance from the surrounding of the system, that if that external disturbance is varying with respect to time, okay, then it doesn't just depend on the system alone, but it also depends on the varying surrounding as well. Okay, so in order to represent that dependency, I'm putting this t explicitly. Okay, so if I put this t explicitly, then the system is known as non-autonomous system, and if that system doesn't depend on t explicitly, then the system is known as autonomous system. See, here t dependence is not there. Okay, but for this course we are going to focus only this form, which means we are going to ignore the history dependent variable, and we are going to consider the systems which only depends on the current state variable. Okay, one example, just a mathematical example, no physical example. Let's say a system which has two state variables, x1 and x2. Okay, and those state variables depend on the rate of change of state variable depends on the current state variables. Let's say it's given like this. Okay, x1 dot is given like this, and x2 dot is given with some other function, which is a function of x1 and x2. Just an example. Okay, this is how we represent the dynamical systems. Okay, now in this example the number of state variables are 2, right? So for some other example, it depends on the system, the number of state variables is going to change. Okay, and that number of state variables are also known as dimension of the system. Okay, so which means this example has a dimension of 2. Okay, because it has 2 state variables. Okay, so one example, spring mass damper system. So spring is there, mass is there, and damper is there. Okay, and let's say some force is also being applied. And now for this system, this is the governing differential equation. But wait, we have told the dynamical system can be represented, or can be represented in this form, but this equation doesn't look like that, right? So is it a dynamical system, or can we represent it in that manner? The answer is it is a dynamical system, and we can represent it in that manner if we do a little manipulation on this equation. Okay, so what is that? So I'm going to assume few things. The first thing is I'm going to assume x is equal to x1, okay, and x dot is equal to x2. I'm going to impose these two assumptions in this equation in the following manner. Instead of x double dot, I'm going to put x2 dot, okay, and instead of x dot, I'm going to put x2, and instead of x, I'm going to put x1, right? Okay, so and if I substitute all these things, then what can I write is x1 dot, which is equal to x dot from this equation, which is equal to x2 from this equation, right? So from that I could say x1 dot is equal to x2. So that's one equation that represents how x1 dot is going to vary with respect to time. And x2 dot, so here we see that this is x2 dot, and by rearranging this equation I can say x2 dot is equal to this one. Okay, so now one question: is this system autonomous system or non-autonomous system? This system is autonomous if the this external force is 0, okay. This external force is 0, then there is no explicit time dependence, then the system is autonomous system. But if the external force, the external influence is varying with respect to time and externally it's being controlled, then the system is non-autonomous system, okay. Fine. Okay, we have discussed what is dynamical system and we have seen few examples. Now the course name is Nonlinear Dynamics. So what is this nonlinear? Okay, now to understand what is nonlinear, we need to know what is linear, okay, because nonlinear is nothing but the things other than linear, okay. So if we know what is linear, then the things which are not linear are non-linear. That's it. Okay, what is linear system? What are linear system? Let's say there is a function, okay, y is equal to f of x, and this function f of x is linear provided it satisfies these two conditions. So what are these conditions? Let's say x1 is one type of x and x2 is another type of x, okay, and if I substitute x1 in this equation, I will get one output which is f of x1, okay, and if I substitute x2 in this equation, I will get some other value which is f2 of x. Now before I put it into this x, I am just adding the x1 and x2 and substituting it into this equation. At that time I will get one output, and that output will be exactly same as the sum of the individual the output of the individual when I substitute independently, okay. So that's what that's one of the property. The another property is x is the input, right? So instead of just giving x, if I scale with a scalar variable c and then substitute, I'll get some value which is f of c of x, and that will be as same as the value for which I'm just substituting x. I'll get an output which is f of x, and then I'm scaling c, okay, and those two things will be same. And if this property is satisfied along with this one, then I can say this function f of x is a linear function, okay. So one example, again a spring mass damper system. This one, let's say there is a function x1 for which I'll get some f, let's say f1, and when I substitute another function x2, I'll get f2. What if I substitute x1 plus x2 in the place of x? I'll get some f which will be equal to f1 plus f2, okay. So then this differential equation is a linear differential equation. However, this equation is not a linear differential equation, it's a non-linear differential equation. You could verify yourself by substituting x1 and x2 and verify whether you are getting the sum of, when you substitute x1 plus x2 in x, you could check whether you are getting t1 plus t2 as t. Okay. Yeah, by doing that you could verify that this is a nonlinear differential equation. And this example is a damped pendulum with an external excitation. It's a torque. Okay, so that's a nonlinear system. Okay, now in the next video what we're going to see is how to solve these nonlinear differential equation using graphical approach. Okay, we'll see that in the next video. Thanks.